All welcome you to the next session of embedded software testing, the series of Unit 2, where we study about testing methods. Uh, Today we study about state or event transition. We continue on that, and we will continue on the other techniques that we have. So before that, we will see what we had studied in session 15. We know that given a range, something like a refrigerator temperature from 3 to 8, we can have test cases. So the earlier session we study about the boundary value analysis and with an example of temperature indicator indicating red and green between 3 and 8. The different test cases. So these are test cases for that temperature range. About 5 test cases are there, taking care of negative, positive, just below the boundary and above the boundary. There is a nominal value also. This is subjective to the requirements whatever we have. State transition, it's purely based on the state based behavior. Mostly these state based machines or state machines are implemented in embedded systems with the help of models. So today we study about the model based testing also. Before that we will try to understand so what are the states that embedded systems can have and how we can test it. So we took an example of a tape recorder where it can have states such as off, on, recording, etc. So 3 important things that we need to remember is state itself, then there is a event. Based on that event, action will be taken care. That means it is in the off state when the tape recorder is off. Once it is powered on, the power on is an event. The action of that is the tape recorder will be powered up and it will start the initialization and initializing the system. So this is basically a fundamental embedded system nature. You take any embedded systems, we have a power up sequence. After power up, we have initialization. After the initialization, there are applications that will be either initialized or triggered, or depending on the type of application, type of embedded systems that we have, it could launch different applications. Then we studied about 2 zones in 2 regions basically, which can switch between states such as this. Then we know that the events or the states transition can be tested with the help of behavior. Then the behavior can be classified into 3 types. One is a simple behavior where the system always responds in exactly same way to a certain input independent of the system's history. So it will not worry about the system's background or history. It will just drive the value or drive to the action based on the input. So that is what is the response for a certain input. Then there is a second type called continuous behavior, where we have the current state of the system depends on the history of the system, such a way that it is not possible to identify a separate state. That means states keep on changing. We will not be knowing it's a continuous behavior of the system. Then we have a state based behavior where the systems enter into different states can be distinguished from other system states based on the system history. So these are the basically 3 types. These are all leading to different functional behavior within the system. All these functional behaviors are underneath the state machines. So we need to cover all this behavior while testing the state transitions. All the entry and exit of each functions and different states, it will be revolving between the states. All these have to be covered. So test cases we need to create reaching each state and seeing the zero switching coverage in terms of transition, Then we have a chain of transition like N to N switching, etc. Then state transition fault categories also be listed. Uh, it, the fault categories can occur in the states. About 5 states faults can be there. Then we have a guards. Then we have transitions. About 4 transitions faults can be there. Then we have events, 4 type: missing event, hidden paths, and reaction takes place, but an identified event is there. Then we have a synchronization issue where multiple regions or multiple subsystems are involved, and there is no synchronization between these two, and states are changing independently. So that also is a fault or a failure. Then we listed out all these fault category in a table, and for coverage purpose we use this table to highlight whether that faults have been covered or not. So, and we have also ticked the state transition technique. Sometimes it may not be possible to do a automation or testing technique. As I said in one of the class, that those could be tested implicitly with the help of analysis or inspection. So that is where categories coverage. We have listed out the checklist and the state transition technique, and some of the techniques we may have to do it manually or doing inspection or some other techniques. So that's why these are not checked here. Okay, so this is supposed to be an exercise for the previous session. Please make a note of this exercise. Write a state and transition test cases for the below. Okay, so I think you have one of the session you have seen there is a requirement which I had given requirements specification for embedded unit instrument. So you can see at different modes I used to say. So now you can consider that modes as states. So there are about 5 states: init, operational, maintenance, download, and fail. So there is a diagram underneath this. You can use this diagram and the requirements which I have shared. Again, I'll share it. For that, you need to write state and transition test cases for the below. You can write a simple test cases identifying the inputs and change in the transitioning of the states, then write an expected output. So that should be the exercise for this session. And I guess some of the embedded system glossary we need to touch. Few I have highlighted here in terms of code coverage. We know that code coverage, how much code we have tested versus the complete code. So which is nothing but the coverage, how much have been covered or executed. The next one is about the component, a minimal software or hardware item for which a separate specification is available. That means a unit. It could be a ECU or in aerospace it is called a CSI, CSU, whatever it is, CSCI, etc. Then there is a term called coverage, the relationship between what is tested by the test set and what can be tested. It is expressed as a percentage. Usually, in terms of percentage, the coverage is spoken. Debugging, all we know in terms of finding and removing the defects, we use this. This is typically a developer's setup that can be used by tester also. Defect is nothing but a fault. Driver is a new term, a skeletal or purpose specific implementation of a software model used to develop or test a component that is called by the driver. That means it's a test driver, it is called. So where we provide the inputs and which will trigger the needed conditions and which can be used to provide the expected output also. So that is where we use a driver, also it is called as a test driver. Then we have dynamic testing, a process of evaluating a system based on its behavior during the execution. This we know, we studied. Embedded software is a basic thing that everybody knows. Embedded system. So basically, embedded software talks about system having controlling functionalities and all that without the hardware. Embedded system has both hardware as well as software, because software needs to work with the hardware. Then we know emulator what it is. So it accepts the inputs for the system and produces the outputs by the system. So that is about the continuation of the last class. So we will see the state or event transition today. So as I said, this exercise we need to do by developing a state and transition test cases for the below requirement. Okay. Now state transition testing technique we will study. So in response to input events, the correct actions are taken and the system reaches the correct state. So that we need to ensure. That is what is about state transition testing. We need to do it. That means should make sure that in our testing we will be providing sufficient inputs. So the correct actions are taken for those inputs, and the system is expected to reach the correct state. The technique is called state transition test technique (STT), as spoken by the book which I referred in the one of the class. The STT consists of the following steps. There are 5 steps that state transition test technique has. Composing the state or state event table. That means we need to compose a state event table. Then composing the transition tree, having all the transitions, having all the state events table is provided. And the third one is composing the test script legal test cases. So we are coming up with a legal test cases. That means the test cases which will drive all this transition path. Then the first test script illegal test cases, which will take care of the negative cases, something like test cases which are not going to happen really in the normal embedded system execution. And the fifth one is a test script gods, as we know, identifying the gods and scripts how we can do it. Okay. Okay. So we need to know about state diagrams also. So we will study about a state diagram in detail with a VCR example. So before that, we will just identify the STT. Which is STT. We know that it's a state transition test technique. Okay. So first step, what we spoke is composing the state event table. Okay. The state chart is the starting point for the composition of the state event table. That means before we draw a state machine table or state to event table, we need to identify the composition in terms of how the state chart is there. So we will take an example of a VCR. Here. So the state chart is the starting point for identifying this example application. So we need to see the composition of the state event table, basically driven from this states first, then the events. So you can see the arrow marks as events and the states in the rectangular boxes. So if a state event combination is legal, then the resulting state of this combination will be incorporated in the table. That means we are going to have a test cases for legal if it is a state event combination is legal. In addition, the transition will be assigned a number. So there is a unique number for that particular transition that is identified in the table. You can see this table. We'll study this. The first column of this table holds the initial state. The other columns consist of the states that can be reached directly from the initial state. One transition away from the initial state also is there. So from the initial state, what are the different states it can enter? So that also needs to be entered. Next come the states that are two states away from the initial state. That means from the initial state next to next state. This also is there, the third state, we can say as an example. So until all the states are represented in this table, we are going to continue on the right hand side. So state event combinations for transition to self resulting the state is accepting state must also be included in this state. That means it can come back also to the initial state. You can see it is going for the standby state. That is one of the initial state we can say. That also needs to be listed. So using the state chart concerning the video cassette recorder, it is there in the previous figure. The state event table is drawn as per this. Okay, so you can see the rectangular boxes having the different states. So we have about 1, 2, 3, 4, 5 states. Okay. So there are about 5 states you can see. So we need to identify those states first. Then identification. Then list out all the events that are responsible for moving to the states. For example, this is the starting point of the state, which will go into a standby upon power up. So in standby state, it will continue till we have, see how many events are there. To go to play, one event is there, and for going to the record, one more event is there. From any other event is there. Rewind, yes. But here should be able to standby. And also there is one more last one is about fast forward. So 4 states it can go based on the events that we have from standby. So one is a play, another is record, another one is rewind, another one is this one. Okay, this is the moving forward phase. Similarly, once we go into play, let's say standby upon power up, we have gone to standby. Next we are going for the play. From play, it can come back standby again if the event of stop button is done. Similarly, from play, we should be able to go to rewind. We know that in a tape recorder or VCR we can do a rewind, and for the fast forward also those buttons can be pressed. So you should do that action for that event. Similarly, directly from the play we can go to standby if the tape is ended. So this is another condition. So interestingly, they have put all the combinations that VCR can take. So this is how it will be designed basically. And taking up more events, let's say we are moving from standby to record. So there is a guard. My tape is in exist and not my tape is in end. That means that my tape is there. Without the tape, it will not record. First of all, that condition is a guard. First, it has to be satisfied. Then there is a event of record button. So these two primary inputs, if they are satisfied, then it will switch to the state where the record state is going to happen. It will keep on recording till the stop button is pressed. So only way to go to the standby is stop button. Of course, there is a tape end because this one of this guard is false, so it will go for the standby. Okay. So taking up another state. See, let's consider about the states within other states. Let's not take the primary state as standby. Let's see how play and fast forward can interchange between them actually. So you can see there is no state from play to record, because from play to record the VCR has to be stopped first, then you can go for the record. Similarly, between play and the fast forward, we have an event called fast forward button pressed in the play condition. So it will go fast forward, and once the fast forward button is pressed again, or the play. So this will be keep on happening. This is what is the continuous behavior what we have seen. For all these events, we are going to draw a table. You can see a nice table written here in the table 11.4 of the book. State event table with legal combinations. These are all legal combinations indicated by a bullet. And any other thing that we want to go through here? Okay. So these are basically the state events that needs to be studied. Once we have the state chart seen, we should be able to draw the table. You can see from standby, rewind button can be pressed. So this uniquely numbered as 1. Play can be pressed 2. Fast forward can be done 3. 4th is record. And similarly, we have standby to rewind as a 5th, and the 6th one is fast forward. 7th is standby. From rewind to standby can go. Similarly, for beginning, okay, 8th as a standby. Means rewinds to standby. You can have to see that way basically. So these columns are different states: record, play, fast forward, rewind, and standby. Similarly, standby. These 5 columns are states, and these 1, 2, 3, 4, 5, 6, 7. 7 actions are there, or 7 events are there. For this event, so what is the state of these states? Okay, so I will try to explain in a little detail. 2, 3, 4, 5. These are different states, and these are the events. Okay. So events: rewind button, play button, fast forward, record, stop, in tape, beginning of the tape. These are all the events. For these events, so what is the stand of these each states? How it is going to take action? Okay. There are bullets, of course. That bullets are nothing but the illegal combinations. So we spoke about legal and illegal, or what is that called, negative or positive, whatever the way you want to uh, term it about. So the illegal combinations are something like which won't have any action, though event is valid as illegal event. The action is ended with illegal event. That means no action is taken care, or the system should not accept that as an event. For example, when the rewind is happening, rewind state is there. There is no point in rewind button, right? So we cannot press the rewind button, or we may press it, but it will not take, or it will not do any action for that. That's the illegal part. Of course, we need to test illegal also. That we need to highlight it, or we need to do a table, event table for that also. And when the rewind is happening, we cannot do a record. Similarly, like this, there are number of illegal combinations. In standby, we cannot do a stop button because it's already stopped, and end tape will not happen in the standby because it is neither rewinding nor playing. Beginning of tape also will not happen. Similarly, while recording is happening, rewind cannot happen, play cannot happen, fast forward cannot happen, the record button itself cannot be pressed, or there is no action for the record button if it is pressed. Of course, it can go for a standby and beginning of the tape it cannot go. That is the illegal combination. And you can see there are two standby, 17 is standby, 18 is standby. So this is based on the events. So this 17, this 18 is different because while the record state is happening, the user has pressed the stop button, which will result in a standby. Similarly, if the record state is happening, if the user has pressed the end tape, or sorry, user will not press, sorry, the tape will end, so that also will enter into standby. Similarly, fast forward will result in stopping the button, it will go for a standby. Fast forward will go for a standby, the tape is ended. So likewise, we need to identify all the events for the state diagram based on the state chart. So it's very important to understand the states and different events. All these events have to be listed out here. So you can see the number of arrows. These are all nothing but the events. So there are about 18 events that are possible with this state diagrams. Okay. So that is the second step. So what we spoke about is composing the state event table. Then we have seen the state events with the illegal combination. Next one is transition tree. So this is very important aspect also, how the transitions are going to happen. So why this is important is, for a tester he needs to know whether he has covered all the paths, different paths, because this fast forward can happen from standby to play to fast forward, or the fast forward can happen between standby to rewind to fast forward. Like this path we should execute. It's not just enough to do a standby to rewind or rewind to fast forward. We need to cover this path, standby to rewind to fast forward. That is why it is not just enough to have the table. The next step after the table is listed, we need to have a transition tree. So it's a very nice picture where you can see the first initial point or the initial state is the basis for driving the transition tree, because all the paths are going to be starting from standby, or for the paths that is on the rightmost side is going to be taken care with the help of the left hand 4 states. So that is how we are going to list out the transition tree. Okay. This tree is drawn basically by understanding the different events and the states that events will trigger. So from standby to, we know that there are 4 states it can enter: rewind, play, fast forward and record. Each substates of standby, that is rewind, play, fast forward, record, can enter into its substates. Like it can go for a play, it can go for a fast forward, it can go for a standby, it can go for a standby. So this path we need to execute. How many paths are there now? Likewise, we need to count all the paths. Like first path is this, standby to rewind. First path is about standby to rewind. Second is standby to play. So these 4 paths are there. Once we have these 4 paths, fifth path is rewind to play. So this is a test path 1. So to execute this test path 1, we need to have path 1 and path 5 done, because standby to rewind to play we need to have, right? Similarly, the 6th path, 7th path, 8th path, like this, the continuous test paths are different. So each paths are legal combinations basically. You can see about 14 paths are there, so which will cover the complete testing of this event. So there is a note guarded. So standby to rewind is with the help of the conditions that we spoke about. If that guard is there, then that state will enter. So others are possible terminal point. That means it may not go beyond that. So you see that fast forward is the last terminal point, and the play is also a terminal point. Standby is not a terminal, because standby again can go to a different path. So likewise, we need to have a transition path defined. Okay. The next, after composing the transition table, sorry, the transition tree, we need to have the legal test cases, right? So the test script we are going to derive for these legal test cases. So how these are drawn is based on the unique identification events in the guard. That means guard also need to be taken care in terms of tape exists, tape not at the beginning. It may be in the middle. Tape exists, tape not at the beginning. This is one of the guard. Tape exists, tape not at the beginning. So all these are key inputs for the event to happen, and for this individual tests or the legal scripts, we have a action. So what is the action? The expected action is start rewind. The state where it will enter, rewind state. Stop rewind. As a result of that, it will go to the next state as play, and the resulting state is play. So the second test case, play button is pressed. What will happen? If it was in a rewind state, it will stop. Then start the play, it will go to the state, play state. Similarly, now stop button is pressed. The play that was the previous state will stop. It will go to the standby. Then we have the rewind button. So likewise, we are going to list out all the legal scripts. We can have any combination of this, but that should be based on this path and the legal events or legal combinations that we have here. Similarly, we are going to have a illegal combinations also. This is continuation of legal combination. There are about 14 legal combinations are listed. Again, each one is again having its own sub events. As we see, test paths 14 are there. So each 14 path can have another inside substates entering and exiting. So all these have to be exercised with the help of legal test cases. Next one is the illegal test cases. So illegal test cases, we know what are those. When the rewind is happening, there is no point in pressing the rewind. Similarly, when the record is happening, these 5 dotted the bulleted items like rewind cannot be done, play button cannot be done, fast forward cannot be pressed, and record itself cannot be done again. So these are all illegal combinations. For each of these illegal combinations, we are going to identify uniquely with the IDs. Illegal 1, illegal 2, illegal 3, like this. There are about 16 illegal events or the combinations that can be done. So let's see how many are there here in this. Yeah, about 3, 3, 6, 9, 12, 16 illegal combinations are there. So same thing is explained here. Setup is L1.1. So what is that L1.1 is? What we have seen here. The rewind button. Tape exists, tape not at the beginning. That means this is the guard, and action is rewind. So rewind state, it is there now. How to reach the rewind state? Rewind button is pressed, and when the rewind is happening, what is the illegal action we are going to have? We are going to press the rewind again. That is what the illegal script. And for initial setup, we don't need to mention any ID because that is the default state. We are going to have stop button or end tape, beginning of the tape will not result in anything. So that is the illegal test case. Of course, we need to exercise illegal test case also. So having this illegal and legal, we have the complete coverage of the state events. So this is the fourth step that we are going to do. So what are the four steps that we have seen? First, we are going to have a state event table. Then we are going to have a transition tree. Then we are going to identify the legal test scripts, and we are going to identify the illegal test scripts. State event table, this is the one. Then the transition tree, then the legal scripts and the illegal scripts. These four steps are very important for drawing the state event. Of course, the last one is being test script guards. We can do that. It is not mandatory, but it is depending on the conditions that is underneath that. But mostly we have covered with the help of this legal and illegal scripts, so we can skip that also. Okay. So while doing this state transitioning testing, so there are certain challenges in terms of its practicality. So what are those? Okay, we'll study about that. So testing hierarchical state charts. That means the state charts can have a hierarchy in terms of main system and subsystems. It may be little impractical to test all those combinations. It could be top down or bottom up manner. It could be there. So it may be difficult to do or achieve the testing hierarchical state charts. So if the like in hierarchy, if details are not much laid out, or the details of the underlying levels are not known very well, so it is more practical to use a top-down approach in that case, because the details we don't know. So we start with a top-down manner, because hierarchical way of doing this is what is been used. Like say we know in this hierarchy we have standby to the next level and the next level. If there is a complex systems which has its own substrates under play or fast forward, and the details of that model is not clear or not known, so then it is difficult to do the bottom up from this onwards. So better to start with the initial or the top down approach. That is what it means. So the super states, it is also called a super state. So that is what it matters for us to test it. So only the incoming and outgoing transition from the super state is very important in that case to identify, to cover as much. But whereas in the bottom up approach, the lowest level of hierarchy is tested first. But if the details are very much available, it is easy to do that. Successively, higher levels of the integration are tested until finally the complete system has been tested. So in complex systems, what will happen is top-down approach may not be possible sometimes, because we may not have the system completely ready, and we have a clarity about low level details only. So in that case, the bottom up approach is suitable. Once we have the integration completely done, then high level hierarchy top down approach can be taken care. Next one is the extensiveness. That means the coverage. As I said, we have different states. We have a legal combination of the scripts that can be developed for the legal state entry and exit, and we have also illegal state event combinations. All these need to be covered in order to have a coverage, but it is very much extensive to have all these 14 or sub 14 paths. The complex systems, it may be a little tricky to have the coverage. Some events it may be difficult to cover, especially the path when you consider if it is a straightforward from standby to play and play to standby, it is easier. But from standby to play and play to fast forward, and fast forward suppose has other substates internally, it may be little trickier or impractical to do that. So in that case, we have to do other methods to overcome this practical issue. That's what it means. So the extensiveness, the effectiveness of the state-based test method can be modified by deciding to what extent the dependencies between the successive transitions are tested. It depends on the method. So the transition can be tested individually in that case, but it is also possible to test a combination of transitions. When it is possible, we should be doing that. If it is not possible, we should be testing it alone. That means each transitions can be executed or done individually. Suppose we may not have a provision, or suppose we may not have a provision to test this part completely, right from standby to play to this. So the best alternative is take the credit of this, take the credit of this, then take the credit of this. First execute this, then try to emulate as much, because we know that play has entered. Try to execute this path, try to test that path. We start with this, we end with this. So one execution is done, then we start with this, end with this, or it could be further next level. So individually we can cover where there is a practical issue we are facing it. So that is what is the extensiveness, the coverage perspective if there are challenges. So we know that test path coverage is the number of path coverage executed versus the total number of coverage, n to 1 switch coverage or 0 to n coverage. All these are coverage percentage we are going to have it as a report. Next one is the fault detection. The state-based test design technique described here is based on the test depth level. So the minimum test effort is required for state-based behavior. Once we have this platform ready, the entire system is based on this, so we don't have to change it again if there are bugs fixed. So we should be able to find the faults easily. But sometimes what will happen is we may have to change once it is fixed right from the beginning. That means to address a fault, single fault that could be in any of the deepest state, we may have to exercise the complete path. So that is the challenge in terms of detecting the fault. So fault categories, all fault categories may be little challenging in terms of testing it. So in that case, individually the different states can be exercised to find the fault and take the credit of the other states which are exercised in addition to this. So we need to have a choices which will help us in isolating the fault based on the table what we have drawn in the earlier slide. Then it is the feasibility. That means whether before I decide the model state based testing, we should have a feasibility whether I can practically achieve. It's very important. So that is one of the practical issues until we test it. That means we may not be able to plan it appropriately. We may have to revise our plan when we really do the testing. So the testing of system state based behavior doesn't always turn out to be simple. Basically, the behavior of a system is hard to determine because the behavior is concealed to an extent, to a large extent, from outside the observation. It could be a different what we see outside than when we start testing it. Embedded systems having object oriented embedded systems or UML type of implementation. So where the data encapsulation are all used, so it may be difficult to test such cases. So an event can lead to a cascade of transitions before the system reaches to a state that can be observed. So we need to know the intricacies of those. So that is where the feasibility we need to do first in terms of understanding that and drawing the transition test mechanism. Sometimes it may be impossible to do it, to distinguish between individual transitions and states at the lower level. So in that case, either we should be doing it with the notion of inspection, analysis, or walkthrough. So that is the best solution what I have observed, where we have a practicality and feasibility. So that those are the practical issues for state transition testing. So it's very important to have a state transition testing because the embedded systems mostly live with state transitions, but there are practical challenges and issues for doing that state based testing. So we need to overcome that with the help of all these mechanisms and best expertise what we can have in terms of system knowledge and the states that we can enter. Okay, so there are that is about state transition testing. We will have the same exercise as what we have here. State transitions testing for this embedded unit, we should be able to do it. Is an exercise for the state transition testing. So what we need to do is we need to have these 4 steps done. Perfect. So let us not consider this mechanism for now. So let us try to do state event table, transition tree, script legal and legal. We have to do it. So that is the exercise for state transition testing. Okay. Okay. There are other types of tests we will study in brief. This is just to highlight in terms of what sort of tests are available. So we will not go in detail. Mainstream usage testing it is called. So this is one of the testing technique. The idea is don't get trapped in testing boundary cases that neglect normal inputs. So this is an interesting thing. Why? Because we strictly go by the theory of testing and all that. So by doing that, we may miss a good value or a nominal input itself. So we'll do all the boundary and all that, but the system fails for a normal range. There is no point in having the testing technique taking credit of that. So we need to have an understanding and have a good test cases basically. So that is what is called mainstream usage. It means the nominal usage of the system we need to have. So that is called as mainstream usage testing. So we will study about now model based testing. So we will have a small introduction session, and we will study what are the model based testing and all that. And we know that model is a behavior of the system. It's as simple as that. So what is model based system? So we know the system is designed with the intent of what is its behavior, what it is going to give a result, what it is going to execute. So what are the elements that it requires to continue its operation smoothly as well as under some of the abnormal conditions. So that is about model. So those finite elements of the system are developed in terms of various models that the system is going to have. The that is what is about model, and model based design is based on that only. So first we do a model based development. The terminology is called. So we have to develop models. So models are developed with the help of MATLAB or Simulink. So this is from MathWorks, and of course there are object oriented C++ supports are also there, like such as Visual C++ supports sometimes developing the models, but mostly it is used or developed with the help of models. SCADE is also another example. Okay, so we have a model. Why? Because it is useful to analyze the system, and it's useful to simulate if there is a problem, or we have a bigger picture of the entire system with the help of models. That is why. So mostly the embedded systems where complexity is involved, they go for model based. The model will have hardware as well as software blocks, like hardware like interfaces such as UART, SPI, SEI, or the Flash, I2C. All this will be part of the model. So all these are part of the hardware, and it also can be modeled. So all those individual units are called as blocks, and those blocks are depicted with the help of models. So for model based design, they use state charts, block diagrams. Maybe we will have a few samples in the next sessions. So the advantage with the tools that we have today, which helps us to develop the models, is that we can generate the code. Not completely, probably to an extent, it will help the user to develop from the scratch instead of developing from the scratch. So it automatically generates the code which can be deployed and verified on the embedded systems. That means we have developed a model, software blocks and some hardware blocks, and with the help of the tool it will generate at least the framework. So how it interacts, what are the parameters and all that. With the help of the framework and some fine tuning with respect to the end target, we should be able to have the end systems. So that is where the advantage of the model based development is useful. So example is MATLAB and Simulink, and Verilog and VHDL they use for firmware for microcontrollers or FPGAs. So where we have a complex systems, this model based development is very useful. So that is why they go for model based design and development. Okay, so once we have the model base available or model based design is developed, we should be able to test. How we can test it? So we can also do the testing of the model with the help of a technique called model based testing, where we apply the same terminology as model based development. Here it is called model based testing. So a model based testing is a process of test generation from models of system under test. So it means we develop the models which will help in doing the testing in terms of generating the test cases or testing it basically. So there are numerous methods that are there are used in the MBT model based testing. We will study a few of them in the next classes. So the test cases are created automatically, same as a development we have seen auto code generation is there. Similarly, we have test cases generated automatically from the models instead of manually. Of course, there are disadvantages also. For complex systems, it is useful where we have time and schedule available. We have a chance to revisit that automated test cases, fine tune it and all that. But whereas the simpler systems where we have a few interfaces and few models are available, it is better to go for manual or black box techniques what we have studied earlier instead of model based testing. So that is advantage and disadvantage. So basically broadly 3 classes are used for model based testing. First is the model itself, then test generation and test execution. How these are all involved for model based testing. So these are some of the advantages. We can have once we have identified the model, how we can verify. At least we have a preliminary understanding of models in terms of whether it is rightly modeled or designed. So it's sort of an early verification advantage. Verification simulated using tests based on high level requirements. That means we can lay out the verification mechanism with the help of high level requirements only. The test can be accomplished on PC instead of target systems. We don't need a target system. We need to have a knowledge of the target system. With the help of that, we can develop the model based testing on the computer only, not on the targets. Okay, so there are other taxonomy overview of the model based testing. So we will study that model based testing and its intricacies in the next class. Okay, to conclude, we will revisit what we have studied and exercise we need to have. So the 4 state transition technique steps we need to apply for the sample embedded unit having 5 modes of states or operations: init, operational, maintenance, download and fail. So we will study about the model based testing and how it can be detailed in the next class.